Hello, and this is going to be our 3-2, where we're going to talk about the Earth's interior, Earth structure, and we're building up on from the plate tectonics idea to the power that's going to be behind plate tectonics, and then we'll finally end up talking about the actual movement of plates and how we know that that's happening. So we're going to start with Earth structure, and we can look at the Earth structure two different ways. We can look at it chemically. We can also look at it physically. Chemically is talking about the type of chemicals like silicon, oxygen, magnesium, iron, nickel, and the composition of the three layers. And if we take a look, we actually have three layers. We've got the crust, we've got the mantle, and we have the core. Now this picture also differentiates the core into the outer core and the inner core. We're not going to do that with the chemical composition because the actual makeup of the core, just like the makeup of the entire mantle and the makeup of the entire crust, is made up of very similar materials. You can equate this a lot of times to an apple, where the crust would actually be represented by the skin of the apple. The meat of the apple is actually the mantle material, and then the core material would actually be like the core of the apple. So the first thing we're going to do is talk about the crust. The crust actually extends from the surface down to a depth of, on average, about 30 kilometers. It's the least dense of all the layers of the Earth, and it's mainly made up of silicates or silicon dioxide, or SiO2 or SiO3 or SiO4. This is actually a model of actually showing the thickness of the crust, and you can see the thickest crust actually occurs on the continents, and the thinnest crust, these very dark maroon colors, actually happen down the middle of the most oceans at the mid-ocean ridges. Underneath the crust is the mantle. The mantle extends from the bottom of the crust, or on average about 30 kilometers, down to almost 3,000, 2,900 kilometers. It's a little more dense, and it's mainly made up of iron and magnesium silicates. So it still has the silicate backbone, but it's actually made up of iron silicates and magnesium silicates. And because it's iron and magnesium, makes it a little bit more dense. It has a density of somewhere up to around 2 times the density of the crust. And then the last layer is the core. Core extends from the bottom of the mantle all the way down to the center of the Earth, and it is the densest of all the layers because it is made up of primarily iron and nickel, although it's got some gold and platinum and other things in there, and has a density of about 3 to 4 times the density of crust. Actually, even more than that. But we have, in terms of chemical composition, the Earth structure is made up of these three layers: the crust, the mantle, and the core. Okay, you've got a data table. I'd like you to fill in. The crust, again, is the thinnest, least dense of all the areas. It is composed primarily of silicon and oxygen for the silicate. The primary mineral, intrusive, is called granite. External would be called anthracite. They are felsic in background, which actually tells you that they've got a silicon type material along with some iron. A density of about 2.7 grams per cubic centimeter. Water is 1.0 grams per cubic centimeter, so this is 2.7 times the specific gravity of water. Throw a rock in water, it sinks like a rock. Take oceanic crust. It's darker in color. It's primarily made up of silicon and oxygen, but it also has iron and magnesium. The primary rock is called basalt, or gabbro if it's intrusive. They are mafic, which stands for magnesium and iron. It has a density of 2.9. It's a little bit more dense than the continental granitic rock, so that actually sits down in the earth a little lower and allows water to go on top of it. The mantle, composed of silicon and oxygen again with more iron and more magnesium, actually is what's called ultramafic and has a density of 4.5 grams per cubic centimeter. So it is roughly twice the density of the crustal rock. And then we go down to the core. Core has a density of 13 grams per cubic centimeter, which kicks into around 5 times the density of rock, composed primarily of iron and nickel. But again, all the most materials, and I guess it's ultramafic, but we don't really call it mafic anymore. And you do have to know that the Earth is density stratified. In other words, it's got layers based on the density of rock, where the least dense is at the top and the most dense is at the bottom, and the other two are in there because of their differences in density. But those are the chemical composition, the chemical layers of the Earth: the crust, the mantle, and the core. If we look at it physically, the layers of the Earth physically, we have 5 layers. We have what's called the lithosphere, and the lithosphere extends from the surface down to about 100 kilometers, and it's made up of the crust and the uppermost part of the mantle and surrounds the planet. It's a little thicker where we have continental crust. It's a little thinner where we have oceanic crust. Then we have, underneath that, we have what's called the asthenosphere. The asthenosphere goes from 100 down to about 700 kilometers, and it is plastic, partially molten, high temperature. Underneath that, we have the mesosphere, and there's the asthenosphere. Under that is the mesosphere, which is the remainder of the mantle. And underneath that, we have the outer core, which is liquid, and we have the inner core, which is a solid. So we start off with a brittle surface. We go down to a partially molten surface, which would be more like silly putty. It moves, if it moves slowly, moves like a liquid slowly, moves like a solid. Then we go down here and we actually get plastic and rigid behavior. And then we go down here, we have mostly liquid because of the high temperature. And then we go down there and we have a solid type material. So those are the 5 physical layers of the Earth's surface. So the Earth can be classified physically and chemically. The physical lithosphere. Lithosphere is cool, rigid, and outermost layer down to 100 kilometers. When we examine the chemical and physical properties of the Earth's layers, we see that a cool, rigid, less dense layer, the lithosphere, floats on top of the hot, slowly moving, more dense layer of the asthenosphere. The asthenosphere is hotter. It is partially melted because of that heat and tends to flow slowly. The mantle is denser and more slowly flowing, part of the slower flowing than the asthenosphere because it's not marketably hotter. We get down to the outer core. We have a very viscous liquid because of the extreme heat. It is iron and nickel chemical composition. And we have an iron nickel, very dense, extremely hot layer, which is the inner core. Looking at it pictorially, composition, we have got the crust, the mantle, and the core, sort of like it is for a baseball or an apple. And physical layers, we do have the 5 layers. We have the lithosphere at the top, the asthenosphere, the mesosphere, the outer layer, outer core, and the inner core. And these are different because of materials. These are different because of the way they act, whether solids or liquids. Here's another picture. I'm talking about the continental crust being a little thicker than the oceanic crust, but then sitting on top of the upper mantle, being the lithosphere, sitting on top of the asthenosphere, which is capable of flowing and probably causes the stress to push these plates around. Studying the Earth's interior requires us to actually take a look at it sort of like we look at inside the person's body with sound waves. But we can use gravity to actually denser layers. We can determine that with seismic waves. Seismology, which actually produced by earthquakes, or we can actually have trucks with very heavy weights vibrate the Earth, but primarily it's made out of seismic waves. They produce what are called P&S waves, primary waves because they're faster, and they're that way because they're more simple wave, and secondary waves because they're the second and they're just a little bit more complex. And we can do seismic tomography, which is actually looking at seismic waves and actually watching them bounce off and bounce into the Earth, and actually take a look at different layers that are inside. So we can actually look for oil, we can look for gas, we can look for coal, we can look for iron ore, we can look for other things inside the Earth. Earthquake waves can be represented by slinkies. If you take the slinky and you push it forward and backward, you watch the compression and expansion, this actually makes what's called a P wave. And the P wave is the fastest of all the waves, and it basically is just a compression and expansion, and because of its compression and expansion it's a size changer, and because of that it travels through liquids who don't like their size change as well as solids. It will not travel through gases because gases don't care about its size. Then we have S waves, and that way you move your hand up and down and you make these waves. This is a more complicated motion. It still travels pretty fast, but it's not as fast as a P wave, so we call them secondary waves. And if you watch that one go across, you can see it actually changes its shape of the Earth. And that can only travel through solids because liquids don't care about their shape changed. And because of that, we can actually differentiate this inside the interior of the Earth because it is either made out of solids or liquids. And these are what are called surface waves. They tend to be the slowest of all the waves, but they can cause the most damage to structure because it's sort of an up and down and compression wave. And if you watch the P wave travels the fastest. The secondary wave, the surface wave, gets there last. Watching those three waves, if we actually had a homogeneous Earth, we would actually notice that the waves would travel at the same speed through the entire Earth, and it would actually travel the same speed all the way through. If we had a gradually increasing density as we go down, we'd actually see these waves refract, and we would actually notice them as looking like this, but what we really see is something that looks like this. And that's because P waves travel through liquids and solids, so they'll actually go through the inner core to make it through the outer core, which is liquid, to go into the inner core, to come back out of the outer, and to come out of the mantle to the other side. And we do have a P shadow wave located right here. And then we have S waves, and S waves are shape changers, and liquids don't care if their shapes are changed. So what they actually do is they get, I don't know what happens to the cursor, they actually get absorbed by the liquid core, so they've got a much larger shadow wave from about 103 to 103, where this one is 103 to 143, and then we get P waves again, and then we get what's called the P wave shadow zone. And because of that, we get a whole Earth looking like this. And if you take a look at this shadow zone, we can equate that to the size of the core. So without even going down there, we know how big our outer core is, and because of the motion of the P waves going through the solid inner core and coming out, we can also guesstimate what the interior, the inner core size is. So this is how we actually look inside the Earth. It's sort of like we use a sonogram to take a look and indirectly find out what's going on inside of our planet. But again, it's caused by the P waves, which will go through solids and liquids, and the S waves, which can only go through solids. And the P wave shadow zone from this one actually says 105 to 140, or the S wave, which goes from basically 105 all the way from one side to the other. And because we get earthquakes at different places, that's only if an earthquake happens up here. If we get another earthquake down here, another earthquake down here, we can actually rotate this thing perpendicular to the earthquake, and we get the fact that we do have roundish layers. Although they're not perfect circles, they're roundish because we can see it from all different directions. Lithosphere. Lithosphere is made up of two different types of crust. We have oceanic crust and continental crust. The continental crust we've talked about is basically a silicate and has 2.7 grams per cubic centimeter for its average density. Oceanic crust is silicates with some iron and magnesium. We get granite rock, intrusive granitic rock, and we have gabbro. But on the surface we really get basalt. But gabbro, which has the average density of about 2.9 grams, they're saying 3, and water has about 1 gram per cubic centimeter. Salt water is a little bit more dense, and we'll talk more about oceanic ocean density when we finally start talking about the bowl that's holding it, and this is one of the last layers for the bowl. Oceanic rock is made out of basalt, which is mafic. Continental rock made out of granite and felsic. Average thickness about 8 kilometers. It can go down to very small, where we're getting the plates pulled apart. It can be a little thicker towards the continent, but average density of about 8. And then the continental rock has an average thickness of about 35 kilometers. Its density is less, so it floats on top of the upper mantle, and the density of this is a little lower, so it actually sinks a little lower. and average density 3 grams per cubic centimeter, average density 2.7 grams per cubic centimeter, granitic and basaltic, granite and basalt, felsic and mafic. The asthenosphere, highly viscous, its resistance to flow, and again it's like silly putty. It flows slowly if it's got an opportunity to do so, and oceanic crust and continental crust will float on top of this asthenosphere, and if the asthenosphere actually has differing motions, it can cause stress in this crust. Oceanic is more dense, it floats lower. Continental is less dense, it floats higher, floats above the water. That's why the ocean is sitting on top of the oceanic rock, and the continental rock is where the terrestrial animals live. And we have what are called isostatic adjustments when the oceanic rock is sitting there and the continental rock weathers and erodes and gets dumped into the ocean, added more weight, and because of that more weight it's like a rowboat, and the boat sinks into the water, or the oceanic crust would actually sink into the mantle, and the continental crust becoming less heavy becomes even less dense and floats even higher, and this will cause stresses in both the oceanic rock and the continental crust, but isostatic adjustments. Empty ship sits nice high in the water. You load the ship, it actually sinks, it displaces the water, and that's why we can get an iron boat, which everybody knows iron sinks in water, but if we fill it full of air, we can make it less dense than the water that it's flowing. Icebergs do the same thing. As the iceberg actually melts, it rises higher, which melts more of the iceberg, but we have about 10% sticking up, about 90% down. Mountains will do the same thing. As long as the mountains are producing new mountain material, it'll sink lower and lower and lower into the mantle, but as the volcanoes that produce the mountain, or the tectonic forces that produce the mountain stop, you'll get erosion, and the erosion will actually dump things down on lower sections, which will push them down. We'll get uplift of the mountain area and will cause stresses in this location. So the continental rock with deposits out in the ocean will actually cause this to be heavier and will sink farther into the plastic asthenosphere, and we'll get the uplift of that continent as the mass gets moved from the continent into the ocean floor. Here's a picture of a cut-up picture of the Earth where we talk about the convection in the asthenosphere, and if we get a very hot section of the mantle, the motion will rise and we'll get these things to move in a opposite direction, making what are called convection cells, and these convection cells will cause stress up in the crust and will cause the crust to pull apart, and that'll allow mantle material to go up to the surface and actually make new oceanic crust. And if it runs into another, because if we push this thing around a spherical object, eventually it will run into this one coming, and we'll actually talk about this with plate tectonics. Okay, the last thing I want to do is I want to show you this. This is a shockwave file which I used to be able to embed into PowerPoints, but Microsoft actually disallowed that with newer versions of PowerPoint or new versions of Office. So here's the link, and it'll probably tell me it's not safe, but you can be sure that it is. It's coming from a college site. And here we go. So we've got a continental crust. We got it moving because the mantle motion. It's going to do the ripping apart. And can I stop this? So we've got mafic material, we have felsic material, we've got molten material in the mantle moving, and it actually causes these two to what's called diverge. It's going to pull this one off to the left, pull this one to the right. It allows molten material to come up, and the fact we'll start getting a valley. Can I rewind this? And let's play it just for a little bit. Okay, we can see we have a river flowing in here, but as this thing gets lower and gets wider, it's going to get filled with a thin ocean. It is a rift valley. We'll have basaltic eruptions inside, that's oceanic crust, and you can see the ocean will get thicker and thicker and thicker. It'll get wider and wider and wider with this divergent, and eventually we'll have a thin ocean and then a bigger ocean, a bigger ocean. This is what we actually think happened with the Atlantic Ocean, where we have North America and Africa together when it was called Pangaea, and Pangaea got ripped apart 250 million years ago. We actually have this larger ocean. Okay, and that is the end of this section, so I appreciate you stopping by. Thank you.